This video is going to be a visual proof of the Pythagorean theorem. So we'll get to this slide last. In order to follow along, there are a few other geometric properties we're going to look at. One involves the comparison of a rectangle and a triangle formed from the diagonal of that rectangle. And this is where we're going to really start, is by looking at a topic called shearing a triangle. So the purpose of this construction here is to demonstrate that if given a fixed base, this segment turning red here, this is the base of the triangle, and notice that its measurement right here is not changing as I drag the opposite vertex of the triangle. The other piece that's not changing is this fixed height, BD here, and this property of base and height being perpendicular, also measured with this angle, is true for any base and height of a triangle. So the perimeter can change and will change as we shear this. So you see that right here I have an acute triangle. I could drag A to coincide with D. That would give me a right triangle. And if I drag it over here, I get an obtuse triangle. The perimeter is changing the whole time, but the area is not. And this is one of the important properties about shearing a triangle, and this is one of the techniques you'll see in our proof. Now, given a rectangle, this is adjustable, a dynamic construction. So for any rectangle that has a diagonal constructed, and then the area of the resulting triangle, this area will always be exactly half of the rectangle area. And we have this ratio, the resulting ratio is always 2 to 1. The rectangle area is exactly twice the triangle, or the triangle is exactly half of the rectangle. So that 2 to 1 ratio is also important when we start looking at the Pythagorean theorem. So a given is that we have a right triangle, and this is adjustable. Right? We could see that this theorem will work for any right triangle that we could possibly construct as long as we have this one right angle. Now, the labeling of A and B will always be the legs. C will always be the hypotenuse. And the hypotenuse is always the longest side. So what we want to do is, given that we square the sides, so let's take a look at those areas. When we square the sides of this right triangle, we are getting 3 areas. This is A squared, B squared, and C squared. So we want to prove that the sum of these 2 areas will equal this area. What we looked at with the rectangles is that if we drew a diagonal for each one of these squares, for A squared and B squared, we would get exactly half of the area of this square. Okay, now step 2 is a shearing of this triangle. What I'm going to do is I'm going to be moving, I don't know if you can see these arrows. This is how I'm going to shear while maintaining this height. So this distance from these 2 vertices that I am trying to get you to see right here, this height will remain constant as I shear and will maintain the same area of the blue triangle. The same thing will happen with this red triangle. The shearing is going to occur. This vertex will be going this way while we maintain this height. So this height will remain constant. This base will remain constant, as will this base. So we will not lose any of the area. So here's what that step looks like. And I can hide the originals. And now these 2 areas are exactly the same as the triangles that we started. And remember, the blue was half of A squared, the red was half of B squared. And that is still what we have for each of those areas. Now the next step is we're going to rotate these 2 triangles. So this control angle is going to rotate my red area that was 1/2 of B squared until we establish this now as the base of that triangle. So we're just redefining which side of the triangle we want to be the base. So this is now the base from here to here. And our height I have measured or sort of located with this red dotted line. So if I drew perpendicular from this base, we could do it right over here if you want. If I am taking this measurement that is perpendicular to the base, this is now my new height of the red triangle. And that will be located with this red dotted line. What we're going to do next is shear this red triangle one more time, but now this opposite vertex is going to be sheared in this direction, following this red dotted line until we're all the way over right there. Okay, now let's rotate the blue triangle with the same goal in mind, that now I've relocated the base of the triangle to be right here, and this measurement, which is perpendicular to the base, is our new height. And again, there will be a shear going in this direction of the blue opposite vertex, going across, and it will end up right here. And when we shear a triangle, remember, we maintain its area. So let's see that step. And so we have maintained that this blue area is exactly half of our a squared. All we did was shear it once, rotate it, and then shear it again. This red area is exactly half of b squared. Now remember what we looked at in terms of rectangles, of which we now have two, which we could pick out of this larger c squared region. If we think of this right here as a rectangle, which it is, we have 4 90-degree angles and opposite sides are congruent. This blue area is half of the rectangle area. Each one of these halves of the rectangle is a squared over 2. If I add them together, I get 2a squared over 2, which is a squared. So that is the area of this rectangle, whoops, right here. On the other side of this dotted line, we have another rectangle. And remember that this red triangle was exactly half of b squared. And because it's also half of this rectangle, we have b squared over 2 and another b squared over 2. And if we add those together, we get 2b squared over 2, which is b squared. And that's the area of this rectangle. This is c squared, and it is also equal to a squared plus b squared.